Okay, so welcome everyone to this edition of BRAG. And today we have Ageu Barbosa Freire from Universidade Federal da Paraíba, and he's going to tell us about HS tangential weakly defectiveness and identifiability of some projective varieties. Thank you, Ageu.
Okay, thank you for the organizers to give me the opportunity to talk here. And this is a joint work with Alex Massarenti and Alex Casarot. And the talk will be divided in three parts. First part, I would like to talk about the HS tangential weak effectiveness problem. We will see that this problem has some relations with the second effectiveness problem in the on other notions in algebraic geometry. And in the second part, I will present a method to study just tangential weak effectiveness using degenerations. And we will apply it to Segre variety. And in the last part, I will talk about I will study the HS tangential weak effective of some fibrations. And let me just say that we will work over the complex number, and X always will denote a non-generated variety in the big N. I would like to start with the second effectiveness problem. We start with X, a non-generated n-dimensional variety, and for a non-negative integer h, we define the h-second variety of X to be the closure of the union of all h minus 1 planes of Pn that is 8 second to X. It means that these h minus 1 planes can be seen as the linear span of h general points in X. By a computation, we can get that the expected dimension of the h second variety of X is the smaller between h times n plus 1 minus 1 and big N, but can happen that the actual dimension of this h second variety of X be smaller than the expected one. When this happens, we say that the variety X is h defective. Let me observe that when a variety is h defective, it means that for a general point in its h second variety, there exist infinitely many h minus 1 planes in Pn that are h tangent to h second to X. And we say that a variety is defective or second defective if the variety is defective for some h. Let me just give an example. The example of the P2, the two variance embedding of P2. We can see this variety as the projectivization of the set of 3 times 3 symmetric matrix of rank K1. And we also can see the 2 second variety of X as the projectivization of the set of 3 times 3 symmetric matrix of rank at the most 2. Therefore, the 2 second variety is given by the zero set of the determinant of a general matrix of this form. And then it is a hypersurface of degree 3 in the Hubble space P5. But if you come to the formula of the expected dimension, we have in this case h equals to 2, and also n equals to 2. We have here 2 times 3 minus 1, which is 5. And also the Hubble space has dimension 5, then the expected dimension must be 5. But we get here the actual dimension is 4. This means that this variety is 2 defective. Another interesting subject in algebraic geometry is that of identifiability. We will see soon that this has the relation with the second defective problem. And for identifiability, we consider a point P in Pn And we say that this point is age identifiable with respect to the variety x if it lies on a unique age minus 1 plane in Vn that is age second to x. And more generally, we'll say that a variety is said to be age identifiable if a general point in its age second variety is age identifiable. Let me just draw a picture. We have age here inside the Pn, non-degenerate, and we consider a point P, and saying that this point is age identifiable with respect to x means that there exist age points in x such that when we take the linear span of this point, the point P is inside this linear span. And moreover, these points are unique. It means that if you consider another age tuple points in X and the linear span of them, the point P cannot be in this linear span. Uh, Weak defectiveness is another problem in algebraic geometry which has relation with the second defectiveness problem. And for weak defectiveness, we consider again x as before, and now 8 general points in x. Moreover, we take capital H to be a hyperplane which is tangent to x at the points PIs. This means that this hyperplane contains the tangent space of x in each one of these PIs. Then we define the H contact blocks of x with respect P1 up to Ph and Pth to be the set of points in X for which the tangent space of X in this point is contained in the hyperplane. Now, we will say that the variety X is age-weak defective if when we take an hyperplane age general satisfying this condition, this is satisfying that this hyperplane contains the tangent space of x in each one of these points here, we have that the contact blocks with respect to this P1, pH, and this general age has positive dimension. In a picture, we have again x, and now we are considering an hyperplane age that is tangent to x in the points P1 up to P8. This means that this hyperplane contains each one of these tangent space. And saying that the variety x is age-weak defective means that there exists a subvariety of x that I will denote by C, for which each point on x satisfy the condition that when you take the tangent space of x in this point P, we have that this tangent space is again inside of the hyperplane H. And this happens for each P that I take on C. Here in my picture, the subvariate C appears to be a curve, but it can happen that that the subvariate have the dimension greater than 1. And the last subject I will talk about that has relation with the second effectiveness problem is that of tangential with effectiveness. And for this, we again consider x and p1 up to ph as before, and we define the 8 tangential contact blocks of x with respect to the points p1 up to ph as being the closure of the set of the points in x for which the tangent space of x in this point is contained in this linear span here. And we say that the variety x is 8 tangential with defective if this contact blocks here has a positive dimension. As I told you, let me just give another picture. We consider now age tangent space in X in 8 different points, P1 up to PH, and we consider the linear span of this of all these linear subspace. Sorry. And we will say that the variety x is H tangential with defective if there exists a subvariety G in X for which when I take a point P on C and we consider the tangent space of X in the point C at the point C, this tangent space is contained in this linear store. Okay, and this happens again for each point we take on C. The same thing here happened. In my picture, C appears to be a curve, but in general, the dimension of this subvariety can be greater than 1. Let me just relate all this notion. We have that age defectiveness implies non-age identifiability, which implies age tangential weak defectiveness, which in turn implies age weak defectiveness. This first implication is immediately because, as I told you in the beginning, if a variety is some varieties named effectiveness, it means that if you take a point in its a general point in its 8-second variety, there exists infinitely many h minus 1 linear subspace of P1 of Pn that is 8 seconds to x that pass through this point we are fixing. It means exactly that the variety is not, this point is not h identifiable. The second implication is not immediately, but it's not difficult to prove. But today I will focus on the other two implications because this last implication is again immediately once that the age tangential contact locks is inside is a subset of the age contact locks for a hyperplane general. Of course, if the tangential contact locks has positive dimension, also the edge contact box will has a positive dimension. None of these implications can be reversed. For example, if we take the example, the Segre product, P1 times P2, we can prove that it is one weakly defective, but it's not one defective. The example is the case of the inverse one of plates in P7. It can be shown that it is 3 tangentially weak defective, but it's not 3 identifiable. And finally, if you embed P2 in degree 6, it will be not 9 identifiable, and it can be shown that this is not 9 defective. Now let me take attention in this first example here. We have one variety that is one weakly defective, but is not one tangentially weak defective. Then one can ask for the smaller s for which satisfying the following property. If we consider a linear subspace of dimension which contains the tangent space in a general point of this variety, I'm considering just one tangent space because we have h equals to 1. Uh, I would like that this S dimensional will be tangent in X in a zero dimensional. But if I consider a general S plus 1 dimensional linear subspace which contains a general tangent space of this variety in a point, the contact locks of this S minus 1 linear subspace will have a positive dimension when we intersect it with X. And from this question, we can generalize it for a general variety X, and we get the notion of HS tangential with defect, which says that if you consider edge points in X general, and we denote it by a linear subspace of dimension S, which we will suppose that this linear subspace contains the tangent space of X in each one of these pi, we define the AGS tangential contact locks of X with respect to P1 up to P8 and the linear subspace pi to be the closure of the set of points in X for which the tangent space of X in these points are contained in the linear subspace pi. And when we take pi to be general, and when we have that this HS tangential contact loss has always positive dimension for pi general, we'll say that our variety is HS tangentially weakly defective. First remark is that this notion generalizes the definition of age tangential weak effectiveness and also the definition of age weak effectiveness. This happens exactly when we take S to be the dimension of the 8-second variety of X, which is exactly this dimension, the dimension of this linear span here. When this happens, we will recover exactly the notion of age tangential weak effectiveness. And if we take this pi to be an hyperplane, this is S to be n minus 1, we get the notion of age weak defective. Let me just give you a picture. Again, I consider an age general point in X, and we are taking pi to be an S dimensional linear subspace of Bn, such that it contains the tangent space of X in each one of these points. Then, saying that the variety X is age as tangential with defective implies that there exists a subvariety C in X, for which, when you consider a point on C, the tangent space of X at this point is also contained in the linear subspace pi. Okay. Then, another remark is that if you consider two non-negative integers s prime greater than s, and we have a variety x which is h as tangentially weakly defective, then this variety also will be h as prime tangentially weakly defective. Okay? Thus, if you take s greater than the dimension of the 8-second variety smaller than n minus 1, we have the relation. We have that h tangential weak defectiveness implies hs tangential weak defectiveness implies h weak defectiveness. And the obvious implications are immediately once that we have the h tangential contact locks inside the hs tangential contact locks, which is inside the h contact locks with respect to hyperplane general. Then, of course, if you have here the h contact locks of positive dimension, the other also will be of positive dimension. With this, I finished the first part of the talk. And to the second part, I would like to start with the definition of oscillation spaces, which is as follows. We consider X an integral projective variety of dimension n, and a point P in X, which we are supposed to be smooth. If we denote by phi a local parameterization of X in a neighborhood of the point P, and we take S to be a non-negative integer, we define the set of X S to be the linear span of all partial derivative of phi of order smaller or equal than S. And we define the S oscillating space of X at the point P to be the closure in Pn of this set here. Okay. Another definition which will be very important for us is the definition of M oscillation regularity. For this definition, we consider X as before, and now M distinct points in X, what will supposed to be general. Okay, and between these M points, I will fix one of them. In this case, I'm fixing the point x1. We also will suppose that there exist rational curves connect each point xi with I running from to n, connect each one of these points to the point fixed x1. And let me denote these rational curves by gamma 2, gamma I of t. Okay. Now, for each t in P1 minus 0, we can consider the S osculating space of the point gamma I of t, the S osculating space of x at the point gamma I of t. Then, for example, here I have the S osculating space of x at the point gamma 2 of t. Here we have the S osculating space of x at the point gamma n of t. And also we consider for the fixed point, we are consider the S osculating space of x in this point. Now, we take then for each t the linear span of all these linear subsets and we denote it by tt. It is exactly the linear span of all these S osculating spaces. S I'm taken to be a non-negative integer. Moreover, we consider the 2s plus 1 osculating space of x at the point x. And as I told you, when we take t in P1 minus 0, we get a family of linear subspace here. And if we take t0 to be the flat limit of this family, we will say that the variety x will have m oscillation regular if this T0, this data limit T0, is inside this higher order oscillating space, which I draw in red. Okay. Let me just observe that a variety which has m oscillation regularity means that we can degenerate m oscillating space of x in different points of a fixed order. Here I fix the order to be s into a single oscillating space of x which has a higher order. In this case, we degenerate m oscillating spaces of order s, m minus 1 oscillating space of order s inside an oscillating space of order to s plus 1. Another important definition for us is that of strong two oscillation regularity. This is a little similar with the last definition, but now we consider only 2 points, x2 and x1, and again we assume that there exists a rational curve gamma of t connecting these 2 points. Then, for each t in P1 minus 0, we can consider the K2 oscillating space of x in the point gamma t and the K1 oscillating space of x at the point x1. Here, K1 and K2 are non-negative integer and this is not precisely equal. They are not necessarily equal. Okay? As before, we take the linear span of these two linear subspace. And again, we take the K1 plus K2 plus 1 oscillating space of x at the point x1. Again, when we take t in Q1 minus 0, we get a family of linear subspaces here. And if you take the 0 to be the flat limit of this family, we will say that the variety x has strong two oscillation regularity if this flat limit T0 is inside this higher order oscillating space here. Let me just observe that we can, there exists a function that take accounts how many tangent space we can degenerate into a higher order oscillating space. For this, we suppose that x has any oscillation regularity. Then the function that take accounts is how many tangent space we can degenerate into a higher order oscillating space is defined as follows. This function takes domains in the image in the set of natural numbers and is defined as follows. Hm of 0 is defined to be 0, and when we take k greater than 0, we write k plus 1 as this form here, and we define Hm of k to be m up to lambda 1 minus 1 sum up to m up to lambda L minus 1. Let me just observe that this function HM computed in a positive number, in natural number k, takes account how many tangent space we can degenerate in a k osculating space, in a single k osculating space of X. Now we are ready to present, I am ready to present our first result with give us a way to study the 8S tangential with defectiveness using degenerations. The theorem states that if we have X as before, and we assume that X has n oscillation regularity and strong 2 oscillation regularity, then we also assume that there exists integer L, K1 and KL, which will be greater or equal than 1. And also we take L general points in X. And finally, we assume that there exists a linear subspace of dimension S that contains T, where T is the span of this oscillating space in here. And finally, we will assume that this linear subspace is not tangent to X along a positive dimension subvariety. This means that the set of points in X for which the tangent space of X at this point is contained in this linear subspace will have dimension 0. Under these conditions, if we set age to be this sum here, we have that our variety X is not age as tangentially with the effect. Let me just give the stack of the proof. Remember that the function HM computed in the natural number Kj, there was the number of tangent space we can degenerate into a Kj in a single Kj oscillating space of X. Then, if you take age tangent space, we can degenerate all this tangent space inside T, which is the linear span of these oscillating spaces here. Then, since we are taking a linear subspace which is not tangent to X along a positive dimension subvariety, and this linear subspace contains a span of all these 8 tangent space we are considering, we will have that to conclude the proof is enough to show that is enough to take only one linear subspace satisfying this. Because the definition of HS tangentially with effectiveness, we need to consider a general linear subspace of dimension S. But here, it's enough to consider only a spatial linear subspace of dimension S. And this will follow from this lemma, which tells that if you take a variety and we denote by delta a complex disk containing the origin, and we denote by gamma t a family of linear subspaces in Pn, and we denote by gamma a linear subspace that contains gamma 0 when we take t to be 0 here, and we assume that we have a linear subspace phi containing this lambda here. We have that the dimension of the singular logs of this intersection here is smaller than the dimension of the singular logs of this intersection here, and we are taking pi t tilde to be a general linear subspace of dimension equal to the dimension of the subspace here we are considering. And this pi t tilde contain gamma tilde for each t. In our case, let me just tell you that this lambda here will be our set T, which is the linear span of this oscillating space, and our pi will be the linear subspace of dimension S, what we are considering. And this gamma t, let me show you a picture. Remember that the function HM tells us how many tangent space we can degenerate into a single oscillating space of order K1. Then here we are degenerate x11 up to x1 18 of k1 points into a point which I'm supposed to be p1. And so we are degenerate hl1 up to hl 18 of kl into a simple point which I'm supposed to be pl. Then in each curve we consider the tangent space in the point when you fix a t in p1 minus 0. And gamma t will be exactly the linear span of all these tangent spaces. Okay? And finally, we just have to define this pt tilde, which will be exactly a general linear subspace that contains this gamma t here. Okay? Then we just apply this theorem here, because here we are saying that if you take a general linear subspace of Pn having dimension s, then the dimension of the contact blocks with x is smaller than the dimension of the contact blocks when we take a particular, a spatial s-dimensional linear subspace. And we see here, we are assuming that this contact blocks has zero dimensional, is zero dimensional. Okay? Then here we have that this is greater or equal than zero, and smaller or equal than zero, then for a s-dimensional linear subspace to contain uh, a general uh, a general span of 8 tangent space, it means that it is not tangent to x along a positive dimension. Okay. Now I would like to apply this theorem to the Segre variety. Let me just recall the definition of the Segre varieties. We consider two R tuples of positive integer, n1 up to nr and d1 up to dr, and the Segre variety associated to these to any tuples is defined to be the product p1 up to pnr, pn1 up to pnr, embedded with degree d1 up to dr. Let me observe that Araújo Massaret research in 2019 proved that this variety has strong two oscillation regularity and N1 plus 1 oscillation regularity. Okay. Now we prove this proposition using explicit computations, and we prove that in the first case, if we take a Segre variety D is the minimum between the di's, and moreover this D is greater or equal than 2, if we take a general hyperplane H which contains this linear span here, which I'm denoting by T, we prove that this hyperplane, which is general, is not tangent to x to the Segre variety along a positive dimension subvariety. This is exactly one of the conditions of our theorem. In the second, we prove that if you take a Segre variety and assume that D1 is the minimum between the i's, and moreover, for each I different to 1, we assume that di minus 2 is greater or equal than d1. Sorry. Then, under this condition, if you take a general hyperplane in Pn that contains this linear span here, we will see that this hyperplane is not tangent to the Segre variety along a positive dimensional subvariety. Then we combine this with the fact, with this remark, which says that the Segre variety has n1 plus 1 oscillation regularity and the strong 2 oscillation regularity. To apply this theorem to Segre variety, he note that our assumption is just that our variety has an oscillation regularity and strong 2 oscillation regularity, and we are considering a linear subspace, who in our case, in the case of the Segre variety, will be hyperplane, contain the linear span of some oscillating spaces, if this universal space is not tangent to X along a positive dimension of variety. In our case, we have exactly something like this, but our universal space are a hyperplanes. Then it is an immediate consequence of the theorem applied to the segment as variety that if we take D to be the minimum between D1 up to dr, and we take H to be smaller than this expression here, we just apply the theorem for the first case here, because here we are considering osculating space, n1 plus 1 osculating space of order d minus 1, then we have n1 plus 1 times the function h n1 plus 1 applied to d minus 1. And in the second case, we have that if h is more than this expression, with d satisfying this condition here, the stable variety is not age-weakly defective. And again, in this second case, we just apply the theorem and use the fact that here we are considered the oscillating spaces of order D in n1 plus 1 distinct points. Let me just observe that, for example, if you write D in this way, then the first part of the theorem here tells that if you take h smaller than this expression, the stabilized variety will be not h with defective. Here I just put the definition of the function h n 1 plus 1 applied to the positive number d minus 1. In the second, if again we write d plus 1 in this way, the second part of the theorem here tells that if you take h to be smaller than this expression, again, here I just put the definition of the function h n1 plus 1 applied to d, we get that the synchronous variety is not h with defective. Knowing it, we have that asymptotically the synchronous variety is not h with defective for h smaller or equal than n1 plus 1 up to the floor of the log of d in the base 2. This is the second part. And for the third part, and the last part, where I will study just tangential with defectiveness for some vibrations, I start with X, a non-degenerated irreducible projective variety, and we assume that this variety identifies a local trivial vibrations whose fibers are projective lines. This means that if you look if you look to X locally, X is of the form W times P1, where W we are assumed to be an affine variety in Pm, and we are considering this product embedded with the Segre embedding. Under this condition here, if we assume this numerical condition, we get that the variety X is not H, M plus H minus 1 tangential with the defective. And as have seen before, this implies that the variety X will also, under this boundary, will also be age identifiable, and under this boundary, age also will be not age defective. The idea now is apply this theorem to the Segre variety. And for Segre variety, we consider the special case when one of the factors is P1. I mean, we are considering that N1 is 1, and this P1 is embedded with degree 1. This is, we are considering also P1 equals to 1. Under this condition, we have a variety which satisfies the condition that is locally a fibration, with P1 as fibers, okay? Then we divide the synchronous variety as a P1 times P up to N2 times P up to NR. And under this condition, we apply the theorem and we get this bound for the non-tangential weak defectiveness of the Segre variety. And this means that under these bounds, the Segre variety also will be age identifiable and you will be not age defective. Let me observe that when you consider the Segre variety, the spatial Segre variety, when we have AP1 as one of the factors, our result implies that this variety X is not age tangential with defective for this bound here, when you take age smaller we put then this expression. Now, if you consider the unbalanced Segre product, this means we are considering Segre product such that and R is greater than this expression here. Albert and Peterson in 2009 showed that this type of Segre product, this unbalanced Segre product, will be not age defective if and only if the age is smaller than this expression here. Okay. Now, finally, observe that when we fix n1 up to nr minus 1 and we take nr to grow, this means that it implies that this expression here on the left side tends to the expression on the right side when you take nr to be greater to the infinity. This is because, for example, in the up part here, for example, we multiply up and down by 1 over nr, and here it does not depend on nr, and here we have nr's under nr, which will be 1, and 1 under nr. And when r tends to infinity, this tends to 0. And here we have just these expressions times 1, which is this. And down, we have here, we multiply here by 1 over nr. Then here we will have 2 under nr. And when nr tends to infinity, this will be 0. And again, for I different to r, ni under nr also will be tends to 0 when nr tends to infinity. Then this just reminds nr under nr which is 1, and here we have 2. And let me just observe that since this expression here, which you get here when nr tends to infinity, is smaller than the bound for the defectiveness of unbalanced Segre product here. Our theorem applied to the Segre variety gives us a sharper asymptotic bond for the non-Segre defectiveness of these varieties. Okay? And this shows that our theorem is good to study the second effectiveness problem. And I think I will stop here. Thank you for the attention.
Thank you, Ageu. Are there questions or comments for Ageu? So have you applied this approach to other classes of varieties like Grassmannians or other interesting from the tensor point of view?
Yes, I tried to apply this last theorem here to varieties, but we can't do it because we can't write a flag with local trivial fibration. This is the only case we've tried to apply the theorem until now. Mm-hmm. Different to the Segre varieties.
Mm-hmm. Are there other questions? Well, if not, let's thank Ageu again.